All right. Thank you, James. As he said, my name is Mike Waters, and I work at Adroll. Adroll consists of the Adroll Group, which is a growth platform company, and a couple of business units, Rollworks and Adroll. These business units basically democratize access to marketing, growth, and advertising products. For example, those ads which follow you around the internet. Sorry about that. I've been using Erlang for about 10 years. It's a good fit for the kinds of things that I tend to work on, which are mainly back-end systems and workflow automation related. My background is electrical engineering, although my focus has been entirely on software systems and not hardware. I'm not going to be presenting any code or demos today. Instead, I'm going to give a short talk and present Adroll's real-time bidding platform, which is implemented in Erlang. Talk about how the scale of that platform presented an opportunity for substantial cost savings, how we were able to capture those savings after realizing that we had a data management problem, how we solved that problem using Erlang, enhanced our solution with Elixir, and then finally talk about a few results. So, real-time bidding. Real-time bidding refers to the process by which advertising inventory can be bought and sold at auction, and those auctions are programmatic and they're occurring in real time. What does all that mean? Suppose you're in your web browser, browsing around the internet, and you wind up on the NewYorkTimes.com. The New York Times, being a publisher that wants to make money, wants to monetize those page views. So it sets aside space in its web pages for ads to appear, and those ad spaces can be sold. And by the way, this is a simplification of this whole process. It's too big to cover here. If you want to know more about real-time bidding, come find me after this talk. Anyway, to sell these ad spots, a publisher such as the New York Times will be integrated with an advertising exchange, which is like a middleman. For the specific page view that you are right now making in your web browser, a request will go to the ad exchange, and then from there, the ad exchange will contact potential buyers in the marketplace, such as Adroll. For each one of these page views, there will be an associated auction, or more auctions perhaps, too complicated to talk about. Anyway, each buyer can potentially respond with a bid price indicating, yes, I am interested in this specific page view that Miriam is making. I'm willing to pay $3 per 1,000 page views. And generally, the high bidder is going to win and win the right to display an ad in the space which was won. This is how it all fits together. Users browsing around the internet wind up on some publisher site. The publisher is monetizing inventory, so it's integrated with an ad exchange, which is integrated with Adroll and other buyers. Our backend system consists of a set of Erlang nodes, and they sit behind some load balancer. Notice that there's a figure of 100 milliseconds here. This is mainly where the real-time and real-time bidding comes from. Like I mentioned, each of these auctions corresponds to page views, at least for web inventory. We have less than 100 milliseconds to receive each of these auction requests, do something intelligent with them, and then submit our complete response back to the exchange. If we take too long, the exchange will throw away our response and we will not be eligible to participate in the associated auction. We'll have wasted our time. So we need to have a consistently low latency method of handling these auctions. And by the way, these auctions are exposed to us in the form of HTTP requests. And this low latency requirement, consistent low latency requirement, is partly why Erlang was selected for this platform. We also have a fairly high volume that we need to handle. As you can see here, the minimum request volume globally was about 700,000 requests per second as of when the screenshot was taken a few weeks ago. And the peak was about double that. And like I said, each one of these requests is one of these programmatic auctions. To satisfy these requirements, our system runs globally distributed. And operating at this scale presents a substantial opportunity for savings, which I will describe in a second. This image is meant to illustrate that our real-time bidding system runs entirely in Amazon Web Services. And this is showing it running in a single region. An Amazon region is like a group of nearby data centers in one part of the globe. And they all have names like US West 2, US East 1, and so on. So requests are coming in, our system is handling them, and is in turn integrated with Amazon services like DynamoDB, S3, and Kinesis. Generally, if some managed Amazon service exists that does what we want, we're going to use it as a building block in our system if the price is reasonable. Notice how there's a bag of money in the top right of this slide. Considering only a single region, this represents the inefficiency which is built into our system and which is present in any reasonably large system. So considering only one region, it's not worth our time to chase after every last bit of efficiency, so we ignore this for now. Now it's a little later. Let's say we've expanded our system and we're running in 2 regions. Naturally, there are now 2 bags of money. Still not yet to the point where we do anything about it, but now several years later, running our system in a globally distributed manner across several Amazon regions, they're starting to add up. And at this scale, this could represent millions of dollars in recurring spend that we are paying to Amazon that maybe we don't have to pay if we could just change a few things about how our system works. But we need to know what to change. It turns out that we had a data management problem. This image represents the storage of advertising profile data for users from around the world in DynamoDB. DynamoDB is a managed Amazon data store, a NoSQL data store, which is arbitrarily scalable in terms of storage size as well as throughput. And what we're actually doing is because we essentially copy and pasted our infrastructure to run across multiple Amazon regions, we had a working recipe, so we replicated it. What we're actually doing is storing data for users from around the world in a set of Dynamo tables and then replicating that set of tables to every region where we operate. And this works, but it's expensive. DynamoDB as a source of truth works well. Much of the time it's quite fast. Here you can see the median full advertising profile retrieval time is about 5 milliseconds. And by the way, an advertising profile is just a set of information that Adderall knows about some user. However, the worst case is quite a bit worse. As you can see, the 99.9th percentile retrieval time is 70 milliseconds. And that's over 2/3 of the time budget we had allotted to handling any one of these requests. So we can't use Dynamo by itself. We put a cache in front of it in the form of memcache. Memcache is pretty good. It's about 5 to 10 times as fast as Dynamo for our own application. However, it's not as scalable, but it doesn't need to be for a couple of reasons. The first reason is that we only care about the subset of users which is active in the current window of time, not the entire set of users anywhere ever. And that distribution changes over time. And secondly, when we read a value from the cache, we want it to be in sync with what's in Dynamo. And we sort of enforce this by having a maximum lifetime on each item that we store in the cache to avoid relying on data that is too old and out of sync, which could lead to bad targeting and pricing decisions. So as a result of those 2 things, we can get away with a much smaller cache relative to our DynamoDB storage size. And we also have a 3rd layer per instance Etscache. It's used in the same way as memcached, except it's not shared. And for us, that's basically a free bonus because we have excess RAM on our nodes. So I mentioned in the ideal case, when we go to look up someone's profile, we would find it in our cache, and the value that we find in our cache would be in sync with what's in Dynamo. If we could make that situation occur all the time, we wouldn't ever need to read from Dynamo, and that's what we decided to do, using an application that looks like this. Here, updates are arriving on our DynamoDB tables and being exposed on a set of DynamoDB streams. And these updates are being packaged up by a new aggregator component, which is basically packaging them together and then broadcasting them to all of our other regions on a set of Kinesis streams in those regions. And if you're not familiar with these services, Kinesis is basically like a managed Kafka platform for streaming data processing. A stream consists of shards, which are basically partitions of the data stream, and they're processed independently. And a DynamoDB stream can be processed in the same way as a Kinesis stream using the Kinesis client library provided by Amazon. So on the read side, we also have a new component, which is reading these updates from our update stream and applying them to what's in our cache. if an update comes in for some profile, this thing will read the profile that we already have cached and then combine them together and then write it back to the cache in a safe, using a safe operation. If a profile is not found in the cache, then it was either evicted for lack of space or it's brand new and we're seeing it now for the first time. Regardless, the contents of our cache are kept up to date with what's in Dynamo, which satisfies the requirement that I mentioned. And as a result, we can get rid of Dynamo from all regions except one and save about 80% of our Dynamo DB costs. Notice, however, that this is a cross-region read much of the time. It turns out that with caches of an appropriate size, about 98 to 99% of our data fits in our cache, and this is an infrequent occurrence. And our bidding platform implements the same logic. So to implement this application, we used Erlang and a little Java. So what this is showing is an Erlang node which has launched as a subprocess an instance of the Kinesis client library's multi-lang daemon. And like I said before, the Kinesis client library is a library provided by Amazon, implemented in Java for processing Kinesis data streams. And the multi-lang daemon is a component of this library which allows for Kinesis processing applications to be implemented in languages other than Java. And this works by obtaining leases on a subset of the shards of a stream. Like I mentioned, a stream is partitioned into shards. And for each one, it will launch a subprocess and communicate with it on standard input and output using a JSON-based protocol. And what we've done is create an open source library which will manage this interaction with the multi-lang daemon and cause it to map each such owned shard over a TCP socket back to Erlang. And as a result, we can process all of our shards in a single Erlang node, as shown here. This is what our processing application looks like. Here we have two shards on which we have obtained leases. The multi-lang daemon has launched two subprocesses, which open sockets back to our Erlang node. And we have two worker processes in Erlang, which are each executing our business logic for each record seen on each shard in sequence. And this is what the supervision tree of this application looks like. This screenshot was taken using the observer application. We have a stream supervisor, one of these per stream being processed by our node, and for us that's between 1 and 10 per node. Each one launches an instance of the multi-lang daemon, which obtains leases on a subset of shards and launches shard processes, which really open sockets back to Erlang. And as a result, we have an Erlang state machine process per each owned shard. And for us, that's between 1 and several thousand per node. And this is what the flow of data looks like. Data coming in on one shard, passing through the multi-lang daemon to an Erlang state machine worker, executing our business logic for each record in sequence. This works well. It's scalable and robust. It scales to thousands of shards. However, there's still some inefficiency built into the system. With the normal Kinesis processing paradigm, at most a single worker can own any shard at one time. So supposing we have a stream with 8 shards and our worker has 16 cores, there will be at most 8 Erlang state machine processes running, executing our code. And at least half of our cores are going to be sitting idle doing nothing. We could address this by increasing the number of stream shards, say doubling or quadrupling them, which is what in fact we used to do, but that's still wasteful. We could also consider creating some kind of work distribution framework that would allow us to decouple the processing of data from a stream from the management of records on that stream. And that's a lot of work. But it turns out somebody already did that work. While we were looking at this problem, we came across the GenStage and Flow frameworks in Elixir. And they turned out to be a ready-made fit for our application. This is what we had before our original Erlang system setup. What we have done is create, also open source by the way, a library that acts as an adapter. It's implemented in Elixir, and it adapts our original system to a pipeline defined and implemented using the Flow framework from Elixir, while preserving our original Erlang business logic. This allowed us to greatly increase our the resource utilization of our system, and like I said, while preserving our original Erlang code almost unchanged. And this is what the new application supervision tree looks like. We again have a stream supervisor, launching a multi-line daemon, launching workers for each shard, connecting back to Erlang. Except this time, each state machine worker in Erlang is acting as a producer for our adapter. And our adapter consists of a set of n gen stage processes. Here, n is the number of schedulers online. This adapter, or this set of gen stages, is in turn acting as a producer for our downstream flow pipeline, which consists of a set of n mappers and some multiple of n of reducers. And our business logic is now executing in each reducer process. This is what we had before, the original flow of data with Erlang alone. And this is what we now have using the flow framework. Records are arriving on one shard, passing through the multi-line daemon to an Erlang state machine worker. Here, a record is going to pass to one of our gen stage workers. This is our adapter. And then from there, because this adapter is basically a producer for our pipeline, a record will flow to one of our mappers. The job of each of these mappers is to basically extract smaller things to be processed from these larger aggregate records. Each of these items is associated with some key, and that key allows each item to be mapped to some partition. And then each partition is going to be processed by some downstream reducer. So in this example, mapper 1 has received a record, and from it has extracted items with keys A, B, and C. Items A and B are associated with partition number 1, so they get handled by reducer number 1. And item C corresponds to partition 2, so it's handled by reducer number 2. And notice that despite processing data from only one shard, we are processing it concurrently, independently of the number of shards. And this is basically the decoupling that I mentioned earlier. When we implemented this, we saw about a factor of 2 improvement in overall system performance, not because of any magical Elixir performance gain, but simply because of this rearranging of data processing. So, some results. Memcache is a big part of our application. I learned a few things about Memcache I didn't know before while implementing this. It turns out that by default, it does not reallocate pages of memory between different slab classes. And because while we were implementing this, we decided to change the representation of data in our cache to a much more efficient format, we ran into this. We were seeing a very high eviction rate despite having lots of free memory, and we also had a poor hit rate. And it turned out to be this parameter, which you can enable, which reallocates pages of memory between different slabs. On Java, Java is not my favorite language or environment, but I think reusing the existing Kinesis client library here was a reasonable decision. It successfully abstracts away a lot of the details of interacting with Kinesis and DynamoDB streams. However, it assumes that all workers are equally capable. This can be a problem if you want to mix and match different worker types. For example, if you're using Spot Fleet on Amazon, or if you're trying to process more than one stream in the same worker group. Each worker is going to claim the same number of shards from your stream. And if one is less capable than another, overall processing can fall behind. On top of this, the multi-line daemon does not gracefully handle failure well. If one of these shard processors fails or exits, all of its siblings will be killed, and processing will need to resume from the most recent checkpoint. I haven't mentioned Python at all, but we actually used it to implement our proof of concept for this system. It was useful in that it allowed rapid incremental progress, but ultimately it turned out to be too slow for our needs. We needed something that would efficiently scale up to handle thousands of shards, and it just wasn't a good fit. It was also difficult to coordinate between workers. Each one of these workers launched by the multi-line daemon is a separate OS process. So for example, trying to rate limit certain parts of our application, we tried using FIFOs on disk. It didn't work so well. Overall, I would say in developing the Python version, it seemed that for every feature we added, the rate of increase in complexity increased, and that's not a recipe for a robust, scalable system. So ultimately, we adopted Erlang. Especially for this application, it's faster than Python. However, it required a larger upfront investment. For example, we had to implement a library that would allow us to interact with and control the multi-line daemon in the way that we wanted. However, I found it to be The system we actually developed turned out to be extremely robust and resilient, very easy to manage its growing complexity. And I think that's in large part due to the design patterns promoted by OTP, as well as the actor model. Finally, we adopted some Elixir, specifically the GenStage and Flow frameworks, which turned out to be a ready-made fit for our application. Like I said, we saw about a factor of two improvement in overall system performance simply by rearranging the way we were data processing thanks to this framework, while using a quarter as many stream shards on our reader application. Overall, it was very easy to get going, calling Erlang from Elixir and Elixir from Erlang, and I'm finding many small niceties as I learn the language, and I'm looking forward to finding more as I use it in future projects. That's it. We have a couple open source libraries, like I said. There's also a blog post on the same topic, and yes, we are hiring.